Hello everyone, I welcome you all to the course UAV Design, and our today's topic is on airfoil selection or airfoil design. Whether we have to design a new airfoil or we can choose an existing airfoil based upon their historical data that we're gonna see today. One of the critical tasks in the wing aerodynamic design is to determine its cross section, that is its shape, which is airfoil. Wing is a three-dimensional component while the airfoil is two-dimensional section. Because of the airfoil section, two other outputs of the airfoil are the consequent of the wing are drag and pitching moment. Apart from these two, even lift is one of the constituent force. There are three terminologies which will be revolving around the airfoil and wing. First one is lift and the other two are drag and pitching moment. The wing may have a constant or a non-constant cross section across the wing. It can be of any cross section. It can be rectangular in plan form, it can be tapered in the plan form, it can be straight rectangular or swept back or trapezoidal based upon the requirements. Requirements in the sense the amount of lift generated, the amount of drag minimized with the cross section. Based upon that, we'll be choosing the airfoils and the wing configuration. There are two ways to determine the wing airfoil section. The first one is the airfoil design, where we start from scratch and we design as per our design requirements to satisfy our design requirements. When we are designing a new airfoil, we are designing it to satisfy our design requirements. And we have the second option, selection of the airfoil, that is selecting it from existing airfoils. The best part of this airfoil selection is most of the data of CL versus alpha, CL versus CD are available, so that based upon those graphs we can study the CL at various angle of attack and we can choose our airfoil based upon the mission. If we have to design our own airfoil, first we have to do it numerically, then we need to test the airfoil in the wind tunnel to get the real-time test data, and these test data will be again validated with computational studies. The design of the airfoil is a complex and time-consuming process and needs expertise in fundamentals of aerodynamics. Since the airfoil needs to be verified by testing it in a wind tunnel, it is expensive too. And in order to select a proper airfoil from the previously designed and published airfoil sections, there are three reliable airfoil sources. The first one, NASA. The second is NACA Aerofoils, and third one, Epler Airfoils. In 1950s, airfoils have been classified by the NACA, the forerunner of present NASA. Earlier, the present NASA was called as NACA. We had airfoils NACA 4-digit, NACA 5-digit, NACA 6 series airfoils, and again, suppose NACA 4 series, for example, 2412 and 0012. For example, this is NACA 4-digit airfoils. This 2412 refers to cambered airfoil, and whereas this 0012 refers to symmetric airfoil. Symmetric airfoil is which will be having two equal halves from leading edge to trailing edge. If we see, this is the chord line, right? Starting from leading edge to trailing edge, This is the line which is the shortest distance from leading edge to trailing edge. For symmetric airfoil, this chord will be exactly at the center. This chord line will divide this surface equal into two halves. And when it comes to cambered airfoil, this is a mean camber line. This is a mean camber line, MCL, which divides the airfoil into two equal halves. This is the leading edge. This is the trailing edge. The shortest distance between leading edge to trailing edge is called chord. And the line which is dividing the airfoil into two equal halves, it is called as mean camber line. Right. So coming back to this NACA airfoil series. So earlier we had NACA airfoils. Now the same NACA airfoils, the NACA is called as NASA. And NACA airfoils, we have 4-digit, 5-digit, 6-digit airfoils. And again, 6-digit airfoils are also called as laminar airfoils, using a 4-5-digit codes. Selecting an airfoil is a part of the overall wing design. And selection of an airfoil for a wing begins with the clear statement of flight requirements. This is nothing but the conditions, how much lift the aircraft should have, at what altitude it will be flying, at what altitude it will be cruising, what will be the density over there, what will be the pressure over there, what will be the CL there, because overall it will be affecting the steady level flight conditions. So what is the role of density there, what is the role of velocity there, and what is aerodynamic efficiency. These statements will be very bold and clear. Based upon that, we will be selecting an airfoil or we will be designing an airfoil. For example, for a subsonic flight, design requirements are very much different from a supersonic flight design objectives. Subsonic flight is something which will be flying between 0.3 to 0.8. The Mach number is a parameter to express the velocity. Mach number is V by A, velocity of object upon speed of sound of that object. So when this ratio is coming between 0.3 to 0.8, it is called subsonic flow, and supersonic flow is greater than 1.2. So if it is between 0.8 to 1.2, this is transonic flow. The Mach number is between 0.8 to 1.2, greater than 0.8 and less than 1.2, it falls under transonic, and greater than 1.2 is your supersonic. So in both categories, like in the subsonic, in supersonic or in transonic, the flight design objectives will be entirely different. Again, if we see 0.3 to 0.8 is compressible subsonic flow, and 0.1 to 0.3 is incompressible subsonic flow. Okay. Coming back to this, the flight in transonic regime requires a special airfoil that meets Mach divergence requirement. The designer must also consider other requirements such as airworthiness, structural, manufacturability, and cost requirements. While designing an airfoil, these requirements plays a key role because we need to design our wing, and the wing spans should be as per the airworthiness requirement, safety point of view. Then structural integrity such that during flight it doesn't break, and it should be easy for manufacturing. It should have the facilities to manufacture such complex wing sections, and it should be cost effective. There are several graphs which indicate the behavior of an airfoil in a flow field, which are employed in a selection of the best airfoil. Aerodynamic theories are applied or wind tunnel tests are conducted to plot such figures for each airfoil. Here this is an example of a 6 series NACA airfoil, which is 633-218 airfoil section. NACA is National Advisory Committee for Aeronautics. So here we can see this is the values on the x-axis and these are the chord values on the y-axis. So here how much it is been clearly plotted here. This is for 6 series NACA airfoil 633-218. The figure 2.4 here, this figure 2.4, this shows about a concept called drag bucket. The figure shows typical variations of drag coefficients as a function of lift coefficient for a laminar airfoil, such as in 6 series NACA airfoils. This is applicable only for 6 series airfoil, also called as laminar airfoils. This is one of the significant graphs which is utilized to decide about the wing aerofoil section. In some airfoils, like laminar airfoils or low drag airfoils, the minimum drag coefficient extends over a range of lift coefficients. This feature is called drag bucket. The extent of the drag bucket and the lift coefficient at the middle of this region are also characteristic features of the airfoil. You see here in this figure, there's the CL versus CD curve. If it is having a bucket, right, if there's a drop here, there's a depth here, right, this is the actual curve, but if it moves like this, right, then a small bucket is formed here. This is the CL at that point, right. So this formation is called drag bucket for laminar flow airfoil, and if it is a regular curve, that is for any conventional airfoil. This drag bucket will form only for laminar airfoils or low drag airfoils. The laminar flow airfoil shows a dip in drag over a range of CL values in comparison with a normal airfoil. The following are the criteria to select an airfoil for a wing with a collection of design requirements. The airfoil with the highest maximum lift coefficient, that is CL max, C suffix L max. Lowercase l represents 2D components like airfoil, and if we have capital letter, it will represent to the wing. The airfoil with proper ideal or design lift coefficient, the airfoil with the lowest minimum drag coefficient, the airfoil with highest L by D ratio, that is aerodynamic efficiency L by D max, which will be very important parameter in establishing maximum takeoff weight for cruise and loiter. The airfoil with the highest lift curve slope, that is CL max, the airfoil with lowest pitching moment coefficient, that is CM, the proper stall quality in the stall region, the airfoil must be structurally reinforceable, and the airfoil should not be much thin that spars cannot be placed inside, because we have to ensure that these airfoil sections are a little bit thick, or there is a proper gap between upper and lower surface such that spars can be installed in that. The airfoil must be such that the cross section is manufacturable and the cost requirements must be considered. The other design requirements, such as, for instance, let's take an example of a jet engine or turbofan engine based unmanned air vehicles, we have to store the fuel. So when we are designing the wing, we have to ensure that the fuel tank can be placed inside the wing in both sections, and the airfoil must allow the sufficient space for this purpose. The fuel tank will be in the wing. Right. So when we are using these parts, we are giving that additional gap such that we can place our fuel tank in this, and so that it can easily pass to the engines. If more than one airfoil is considered for the wing, the integration of two airfoils in one wing must be observed. Like previously, in the previous lectures, we have seen geometric twist, aerodynamic twist. Right. In some cases, the this is the root point of the airfoil, root point of the wing, and this is a tip. If these two are different airfoils, root airfoil is different and tip airfoils are different. So how we gonna integrate them? Even that has to be observed very carefully. The calculations has to be done accordingly, and we have to ensure that it is structurally integrated very solidly. The NACA 4 and 5-digit airfoil sections are not very efficient, but 6 series airfoils are the best among the NACA airfoils. The 4 and 5-digit airfoil sections, for example 2412 and 23015, were designed simply by using parabola and line. They were not supposed to satisfy major aerodynamic design requirements such as laminar flow and no flow separation. However, the 6 series airfoils were designed to maintain laminar flow over a large part of the chord. Thus, they maintain lower minimum CD compared with 4 and 5-digit airfoils. The 6 series NACA airfoils are designed by 5 main digits and begins with the number 6. The Reynolds number has a huge impact on airfoil and wing aerodynamic performance. This is becoming more and more important in UAV industries, which operate at much lower Reynolds number than 3 to 9 million, where most of the data are found. In general, the MLR airfoils are generally for very low Reynolds number, and the NASA low speed airfoils, example LS0413, and mid speed airfoils, example MS0313, are for moderate Reynolds numbers. The airfoils which are designed computationally should always be tested in the wind tunnel before using in flight. It is assumed that an airfoil section database such as NACA or MLR is available, and the wing designer is planning to select the best airfoil from a collection. The procedure to select an airfoil for the wing is recommended as: determine the average aircraft weight in cruising flight. We will be using steady level flight conditions there, L equals to W, T equals to D. So from this W, we will get all the parameters. If we know this weight, it becomes very easy to estimate the required CL. So we know the lift equation from our previous lecture. It is half rho V square S CL. And if you know the weight, average weight, it becomes very easy that the amount of weight which will be cruising during the flight, this is the cruise phase. So here, during the cruise phase, how much CL is required by the wing, by the unmanned air vehicle, that will be known if we know the weight. This will help out to estimate this CL. Calculate the aircraft ideal cruise lift coefficient. Once CLC is calculated, calculate the wing cruise lift coefficient, because automatically the span will change, because from an airfoil, from Unity, there will be a span. It might be 2 feet, 3 feet, 10 feet, depending upon the configuration of the aircraft. Then we'll calculate the wing airfoil ideal lift coefficient, that is CL. And after that, we'll calculate the maximum lift coefficient of the wing, that is CL max. Once fifth step is done, we'll enter into the sixth, where we'll calculate the wing maximum lift coefficient, and then we'll be calculating the wing aerofoil gross maximum lift coefficient, that is CL max gross. We'll select or design the high lift device, for example, the flaps, ailerons, elevators, rudders, any other primary or secondary control surfaces which we are using here. We'll check the performance of that and then we'll integrate it. We'll determine the high lifting device contribution to the wing maximum lift coefficient. After that, we'll calculate the wing aerofoil net maximum lift coefficient, and we'll identify the airfoil section alternatives that deliver the desired CLI. This desired CLI is estimated at step 4 and CL max at step 10. These both are very essential steps. If there is any changes in this, then again we'll go back to the step 1. Among several acceptable alternatives, we select the optimum airfoil section by using a comparison table. Conclusion for today's lecture. Airfoil selection or design is a fundamental step in aerodynamic wing design. The choice of airfoil significantly influences the aerodynamic performance of the wing by affecting drag and pitching moment characteristics. Understanding whether to select an existing airfoil or design a new one depends on the performance requirements of the aircraft. A well-chosen or well-designed airfoil ensures optimal lift, reduced drag, and improved overall efficiency. With this, we conclude our today's lecture. These are the references which were used in this lecture. Further, we'll meet in the next lecture. Thank you.